Good evening to all of you, dear participants, and dear Manjil, dear Sarfraz. Welcome you all the last day of the 3 days international webinar on fundamental mathematics. As you all know, we have today we have Mr. Sarfraz Ahmed with us. Mr. Sarfraz Ahmed is an assistant professor of Kaziranga University, and he's doing his research on mathematical biology. Today, he is going to deliver a talk about the basics of differential equations and its application in biology. So I welcome Mr. Sarfraz to kindly deliver his continued session. Please, sir.
Thank you, Dimpal. Before I start my presentation, I specially thanks to Dr. Dimpal Mahanta, the HOD Department of Mathematics, for giving me an opportunity to be a resource person. My heartiest thanks goes to Dr. Biju Kumar Datta for constantly supporting me in every aspect. Last not the least, my special thanks goes to the Dean of SBS, Dr. Zenta Kumar Sharma sir, and all my colleagues, and especially Dr. Manjil Saikia. So now I'm going to start my presentation. So now I'm going to start my presentation, Basics of Differential Equation and the Application in Biological Science. My name is Sarfraz Ahmed. I am from Department of Mathematics, Assam Kaziranga University. So that means my whole presentation is divided into 6 parts. Introduction of differential equation, invention of a differential equation, formation of differential equation, ordinary differential equation, method for solving ordinary differential equation, real-time application of differential equation. Introduction. What are differential equations? Calculus, the science of our rate of change, was invented by Newton in the investigation of natural phenomena. Many other types of system can be modulated by writing down an equation for the rate of change of phenomena. So that means differential calculus is derived from the differential equation is derived from the calculus. What do you mean by the calculus? Calculus is a small stone. So that means differential equation is useful in every day-to-day life. So that means in our day-to-day life, the differential equation play a major role. For example, I have written here, escalation of curve, population increase, chemical change of some kind, locus of football. So that means everything we can capture in a simple differential equation. So now, history of differential equation. So origin of differential equation, who invented, idea, background idea. In mathematics history of differential equation, trace the development of differential equation from calculus itself is independently invented by English physicist Sir Isaac Newton and the German mathematician Gottfried Leibniz. So that means differential calculus and differential equation. That means equation is derived from the differential calculus. So, and it is invented by the English physicist Sir Isaac Newton and later by the German mathematician Gottfried Leibniz. The history of the subject of differential equation is the concise form of synopsis of the recent article. The history of differential equation is 1617 to 1950. So that means this is a brief description about the differential equation, where it from derived. So these are the two great scientists, Sir Isaac Newton and Gottfried Leibniz. So before, I'm going to give a simple definition. What do you mean by the slope and rate of change? So if a line cuts the x-axis or y-axis at an angle theta, then angle is called an angle of inclination. If I express that angle in terms of tan, then it's called a gradient or slope. So that means here, slope means change in y divided by change in x. So this is a simple diagram I have taken. This is x-axis, this is y-axis, and I have taken one line. So that means this is the change in x, here in change in y. We can find an average slope between the 2 points, but how to find the slope at a point? There is nothing to measure, but with the derivative, we can write slope change in y divided by change in x. That is what del y by del x. So all we know, what is a differential equation? All the definition you know, but here I'm going to give a simple definition of a differential equation. So what do you mean by the differential equation? A differential equation is an equation with a function and one or more of its derivatives. So that means it's a combination of differential coefficient, dependent variable, and independent variable. So that means it's a combination of these things and it form a new equation. That equation is called a differential equation. Here dy by dx is a differential coefficient. So in a differential equation, one thing is very important. That means formation of a differential equation. So how can you form a differential equation? So that means before we are going to form a differential equation, that means the method which are used to form a differential equation. There are different methods. One of the method is what you have to remove the arbitrary constant. So that means if I give you one equation, so that means I'm going to tell you, so you have to form a differential equation. So how can you form it? First, you see the constants. So how many constants are present in the differential equation? First here, I'm taking an example, y is equal to mx. The equation of a straight line passing through the origin, or we can say this is a familiar straight line, y is equal to 1 mx. So now I'm going to form a differential equation. So how can I form it? First, you are going to differentiate y with respect to x. I'm differentiating with respect to x. dy by dx is equal to m. So that means here I'm getting m with a constant. So your aim is to what? You have to remove the constant. So now I'm replacing this m by y by x. In place of m, I'm writing y by what? X. So if I write it y by x, after simplification, I'm getting one equation. That equation is what? X dy by dx is equal to y. This is a differential equation of first order. One thing we have to remember. So that if it's contain one constant, then we can form a differential equation of first order. If it contains two constant, then it can form a differential equation of what? Second order. So here I'm seeing one example. Y is equal to a cos x plus b, where a and b are the arbitrary constant. So that means if a and b be the arbitrary what? Constant. So that means your aim is to what? Here I am taking one example. Y is equal to a cos x plus b. So where a and b be the arbitrary constant. So that means how many arbitrary constants are present? Here two arbitrary constants is present. So that means you have to remove the two arbitrary constants. So that means how can I remove these two arbitrary constants? By differentiating twice. How many arbitrary constant is here? Here is two arbitrary constant a and b. So that means we can form a differential equation of second order. So if it contains two arbitrary constant, then you can form a differential equation of second order. If it contains three arbitrary constant, then you can form a differential equation of third order. So that means in this way we can form a differential equation. So that means if it contains n arbitrary constant, we can form a differential equation of what? Nth order. Now, my next slide is solution of differential equation. So what do you mean by the solution of a differential equation? A solution to a differential equation is a function y is equal to fx that satisfies the differential equation when fx and its derivative are substituted into the equation. So that is in this way we can find out the solution of a differential equation. So there is a different method. So that means different method is there. So that means that method is method of solution. So one of the different method is there. So separation of variable, integrating factor, series solution, integral transformation, Lie group theory method, etc. So that means I'm going to give you some brief definition about the separation, different type of method of solution. So what do you mean by the separation of variable? So that means we can use this for the first order differential equation. If I get the differential equation in this form, dy by dx is equal to fx and gy. So that means if I get the differential equation of that form, we can solve with the help of separation variable method. So let me integrating method. In what type of differential equation you are going to use integrating factor. So dy by, if the differential equation is in the form of dy by dx plus by is equal to q, then it is called a differential equation. It's a linear differential equation and it's a differential equation of first order. So that means here we are going to use the integrating factor method. So Here we have to find out the integrating factor. So your integrating factor is what? E to the power p dx. So with the help of integrating factor, we can find out the solution. Now there is a series solution. So that means any differential equation which can be written in the form of p naught x d square y by dx square plus p1 x dy by dx plus p2 x y dy by y is equal to what? 0. This is what equation I'm giving to you. So that means this equation can be solved with the help of series solution. Series solution method where p naught x are the polynomials. So that means how can you solve it? First, your aim is to what? You have to see whether it contains an ordinary point or singular point. If it is containing an ordinary point, then your power series is y is equal to summation of r is equal to 0 to infinity a x to the power r. So with the help of the power series, we can find out the solution if it is an ordinary point. So that means if I get the equation, that means it contains singular points, and then your power series will be y is equal to summation of r is equal to 0 to infinity a r x to the power m plus r. So that means with the help of that power series, we can solve this type of differential equation. That means your differential equation should be always in the form of p naught x d square y by dx square plus dot dot equal to 0. P naught should be a polynomial. So now the integral transformation. So the in integral transformation, the Laplace transformation is there. So Laplace transformation is just like a Xerox machine. So if I put the differential equation, and you can get the what? You can get that equation in an algebraic form. So that with the help of some integral transformation and other transformation, for example, that transformation, we can solve the differential equation. Lie group theory method, etc. So we are going to discuss Lie group theory method later on. So now, what's the difference between a partial differential equation and an ordinary differential equation? Partial differential equation is used to difference mathematical function having more than one variable in them. For example, if I take it z is equal to fxy, z is a function of fxy. So this is about how many variables are contained in it. So there is two variables, so x and y. So that means this is called what? This type of equation we can form a partial differential equation. So what do you mean by the ordinary differential equation? What is the difference? It contains only one variable. So that means in one it contains two variables, in another one it contains one variable. So that this is the basic difference of a partial differential equation and ordinary differential equation. So now my next slide is a shortcut technique to solve a differential equation. So that means you can solve differential equation in different method is there. So that means lengthy process is there. That means time consuming process is there. So that means there is different methods is there. With the help of that, we can solve the differential equation. So that means today I'm going to give you a shortcut technique to how to solve a differential equation within a 5 to 10 seconds. So that means if I give you 5 to 10 seconds, can you solve a differential equation? So let us take an example here. So if I take the differential equation in this form, dy by dx is equal to m ax plus minus b plus minus c and ax plus minus b plus minus d. So that if I give you differential equation in this form, so how can you solve it? So that within a fraction of seconds. So if I give you 10 seconds, can it possible? Yeah, it is possible. Let's see. First, I'm going to give you the working rule of this one. So what will be the working rule? The first step is what? Take the coefficient of x and y, x minus y from the down. Second step is what? Find the determinant to get the solution. So now let's take an example. Dy by dx minus x minus y plus 1 and x minus y plus 1. So this is the differential equation I have given to you. So that means if I give you this differential equation, can it possible to solve it within a fraction of a second, within a 5 seconds? Yeah. So that means first here what coefficient are present here. So here the coefficient is what? X minus y. And what are the variables are present here? X and y. So first you have to remember, you have to write it here, x, y. So that here x minus y is here. So you have to put it here, x minus y. What is the coefficient of x minus y? So here is downward is 1. So you have to put it here 1. What is the coefficient x minus y here? Minus 1. Just put it here minus 1. What is the value of the constant here? 1 here 1. So you have to put it in here 1 and 1. So now here x minus here y is putting, so that means you have to find out the value of x minus y. So that means what is the value? 1 minus minus 1. So I'm getting here 2. Here 1, 1, 1 minus 1. So it gives you what? 0. Yeah, I'm getting this value. So now we have to find out the determinant x 1 y minus 1. So if you want to find out the determinant, so I'm getting the determinant value will be x minus 1 minus y minus. Now again you have to find out the determinant between 1 1 minus 1 1. So I'm finding out the value. So first you have to find out the determinant of this one, then you have to find out the determinant of this one. So if I get the determinant of this one will be this, then this one will be this, so you have to divide it. So one thing you have to remember in case of this one, that means in case of this type of function, the answer is always coming in logs. Why? We know the integration x by x is always gives you what? Log x. So that's why you have to put here log. So here the coefficient is given x minus 1. Just put it here x minus 1. Here the plus 2 is there, so you have to put it plus 2. So that means here plus, here it is given 0. You are finding the value 0, so you have to put it 0. So equal to 0. So this is the solution of this differential equation. If I give you any differential of this one, so you can solve it within a fraction of a second. So I'm giving you another example. Just see this example. Dy by dx, just you think of it. I give you 10 seconds. Within a 10 seconds, just give me the answer. I'm waiting for you for your answer. Just give me an answer. Did anyone get answer? Did anyone get answer?
No.
So I'm going to give you the answer. Just think of it. This one, you know. Here again you have to write it here the x and y. So I'm putting here x and y. So that means this is x and y. So here x minus y. Just put it x minus y. Here what? Downward coefficient is 2. I'm putting here 2. Here the downward upward coefficient is 1. So here to put it 1. So that means x, y. So that means you have to find out the value of x minus y. So 2 minus 1, 1. So again here 5 minus 3 is equal. So now we have to find out the determinant between what? X to y, 1. So I'm finding out the determinant x to y, 1. So I'm getting this one. So again, you have to find out the determinant of this one. 2, 5, 1, 3. So I'm getting this one. So again, we have to get in log. So that means always the answer coming log. So that means
So further, sorry to interrupt you. But
hello?
can you be quite louder because your voice is not very low.
Louder.
Yeah.
So that means first here, that means I'm giving the differential equation in this form. Dy by dx is equal to x minus y plus 1 divided by 2x minus y plus 5. So that means here I'm putting x, y. First you have to write it here the x and y of the variable. So you just put it x and y. So I'm putting here x and y. So that here the downward coefficient is what? 2. So you have to put it here 2. Here upward coefficient is 1. You have to put it 1. So now x, y. So that means you have to write it x minus y. So x minus y value is what? 2 minus 1 is equal to 1. Then 5 minus 3 is equal to 2. Now you have to find out the determinant between x to y 1. So if I want to find out the determinant between x to y 1, so I'm getting this one. Again, I have to find out the determinant between 2, 5, 1, 3. So you have to find it out, the determinant value. So I'm getting the value will be 6 minus 5. So first determinant divided by second determinant, then always it comes in log. You have to put in log. So here x minus y. So put in x minus y. Here x minus 1 value is what? 1. You have to put in 1 plus 2. So that means this one is a plus 2. So put it plus 2 is equal to 6. So this is your solution of this differential equation. So within a fraction of second, you are solving this differential equation. Now, application of differential equation. So that means where we can apply differential equation and what are the importance. So that means in day-to-day life, differential equation is very important. So that means it is used in every part of our daily life. So now we are going to see where the differential equation is very important nowadays. So now the rate of change in the temperature of an object is proportional to the difference in temperature between the object and the room temperature. So with the help of Newton's law of cooling, so we are going to find a temperature in the cup of a coffee. So that means in the morning you are taking a cup of coffee. So after some time it becomes cold. So that means now what is the temperature of that coffee that we can find out with the help of Newton's law of cooling. In that Newton's law of cooling, differential equation are used. Just see Newton law of cooling. So heat lost to the surrounding air is proportional to the temperature difference between the object and the air. The proportionality constant involved the surface area multiplied by heat transfer coefficient. So that means if I capture that thing in a differential equation, that differential equation is given by this form. dq by dt is equal to minus HA T minus T room. That means that will be the T temperature of the room. So that means what is the amount of heat in the coffee? So that means amount of heat in the coffee is always what? Q is equal to V rho CT. What is V? V with the volume, rho with the density, C with the specific, and T with the temperature. So with the help of this equation, this dq by dt and Q equation, we are going to find out the temperature of the whole coffee now. That means I'm getting here dq by dt is equal to minus HA T minus T room. So that means what is Q? Q is nothing but an V rho CT. So I'm going to differentiate this one with respect to say T. So if I differentiate this one with respect to T, I'm getting what? V rho C dt by dt is equal to minus HA T minus room temperature. So now I'm rearranging this one. So if I rearrange this one, so I'm getting what? dt by dt is equal to minus alpha T minus T room. So that means what is alpha? Alpha is what? HA V rho C. So with the help of initial condition, we are going to find out the temperature of the whole coffee. So that means d by dt is equal to minus alpha T minus T room. So this is a simple differential equation of a first order. So this differential equation we can solve with the help of variable separable method. So that means dt here T minus T room. So you have to take this to this side and this one to this side. So that after that we have to integrate. So we are integrating this one. After integration, we are getting the value ln is equal to, this is log temp T minus T room is equal to minus alpha T plus C. So that means I'm removing this log. So I'm getting in this form. So that means after that I'm getting this one. So we are using the initial condition. Your initial condition is what? T0 is equal to T initial. So I'm putting that value here and rearranging that things, and I'm putting the value of A will be this one. That means I'm considering this value is equal to A. So after that I simplify and put in the value here. So that means what we can get we can get the temperature of the coffee now. So that means in this way we can find out the cup of a coffee. That means temperature of the cup of the coffee when it becomes cold. So that means this is the simple application of a Newton law of cooling. So that there are other different application of Newton law of cooling. For example, investigation. It can be used to determine the time of death, computer manufacturing, solar water, calculating surface area of an object. So that means why differential equations are useful. So that means in our world things changes and describe how they change often end up as a differential equation. So that means now pandemic situation is there. So that means all day by day we are getting the COVID cases. So that means how many COVID cases, that means how many coronavirus affected in a day. So that means that can be also find out with the help of mathematical model. So that model is given by what? Logistic growth model. So in the logistic growth model, there is a differential equation I use. That with the help of that we can find out how many people are infected in a day. For example, I have taken here a logistic growth model can be used to track COVID-19 outbreak. In the coronavirus cases, this maximum limit would be the total number of people in the world, because when everybody is sick, the growth will necessarily diminish. So here, just see the logistic growth model defined by the differential equation. So dy by dt is equal to what? Ky1 minus y by l. So what is Y? Y is a community count of infected cases at time T, and K be the continuous growth rate, L the limit to growth. So this is the simple differential equation. If we can solve this differential equation, we can find out Y. So that means what is Y? Y be the infected case at a time. So that means differential equation. Again, I'm telling you the differential equation used in every part of life. So now my next slide is what? How differential equation are used in blood flow. First, I'm going to see magnetic effect on blood. So let's see one video.
Hi, one of the questions I most commonly receive,
Dimpal, it is
especially
audible?
on my latest video where I unbox some extreme magnets,
Hello?
is in this video I'll show you how blood
Yes.
reacts to a magnet and try to explain why it reacts in such a strange way. Alright, first of all, is there iron in our blood? Yes, there is, but not as solid metallic pieces of iron like these filings. If it was, we would definitely be in trouble near a magnet. Let me just demonstrate with water and red food coloring. Without iron particles, the blood runs smoothly through the tube and past the magnet. However, when I add solid iron particles, the iron builds up and forms a clot near the magnet in the simulated blood vessel. This would give you a bad day. Luckily, as mentioned, iron is not present like this in real blood. Instead, it is part of a big molecule, the metalloprotein hemoglobin. Hemoglobin is the red part of red blood cells, and it is responsible for carrying oxygen around your body and removing carbon dioxide from it. It is a very complex molecule. For comparison, around half of our blood is just water. A water molecule is made of 2 hydrogen atoms and 1 oxygen atom, giving it the chemical formula H2O. A simple and easy to remember molecule. Hemoglobin, on the other hand, is way more complicated. It is made of, hold on, let me get this right. 2,952 carbon atoms, 4,664 hydrogen atoms, 832 oxygen atoms, 812 nitrogen atoms, 8 sulfur atoms, and 4 iron atoms. 4 atoms. Our blood isn't exactly crammed with iron. For an average human body, the total amount of iron is around 4 grams with 2.5 grams in the blood. But does any iron content mean that the material will be magnetic? Let's test some common materials with different amounts of iron content. First up is matches. These contain a tiny amount of iron as ferric oxide, an impurity in the match head. Not enough iron to have them stick to a magnet, but on a sensitive water bath they are slightly drawn towards the magnet. Now, if I do some chemistry to them by setting them on fire, something changes. There's the same amount of iron atoms in the matches, but the ferric oxide was reduced to pure magnetic iron in the fire. This gives us a clue. Iron atoms don't always have the same magnetic properties. It depends on the whole molecule. Even this fork, made of stainless steel, which is mostly iron, has different magnetic reactions depending on which end I test. The elements in stainless steel can form different crystalline structures. The cold work done to the tines changed the crystalline microstructure slightly, making them more magnetic than the handle. Still not very magnetic, even though there's a lot of iron in this fork, so much more than in any matches and blood. Alright, based on these tests, I don't like to bleed, so I went to the local butcher and bought some food-grade blood from a pig instead. Perfect. Let's test it with the monster magnet right away. This magnet is insanely strong, but I don't see any movements in the blood. Let's use a small amount on the revealing water bath. As a control test, I will test the empty container first. Seems neutral enough to be negligible. Time to fill it up without making too much of a mess. Here we go. Did you guess how it reacts? Not what I expected. It seems to be repelled by the magnet. I honestly have trouble holding this 12 kilograms monster steady, so let's confirm with the lighter sphere magnet. Yes, the blood is definitely repelled by a magnet. This is called a diamagnetic reaction, but how is this possible with iron in the hemoglobin? Well, magnetism is a quantum mechanical effect, scaled up to be noticeable to us. Quantum mechanics, however, does not compute well with our everyday logic. Very simplified, magnetism is an interaction between unpaired electrons moving in the materials. Paired electrons will sort of cancel out their magnetic dipole moment by having opposite spins in the atoms and molecules. Only unpaired electrons will have a net magnetic moment reaching beyond the atoms and molecules. So, roughly speaking, we can determine the magnetic reaction of an atom, molecule or crystalline structure by counting the number of unpaired electrons in it. In hemoglobin, the number of unpaired electrons in the iron atoms actually change, depending on whether it is oxygenated or not. The iron atoms in deoxygenated hemoglobin each have 4 unpaired electrons, making it paramagnetic and a little attracted to a magnet. The iron atoms in oxygenated hemoglobin turns out to have only paired electrons, no unpaired. This gives oxygenated hemoglobin a diamagnetic reaction. It is repelled by a magnet despite the iron content. The ratio between oxygenated and deoxygenated hemoglobin is typically like shown on the screen. Most of the hemoglobin in our blood is in the diamagnetic oxygenated state, being repelled by a magnet. The water making up half of our blood is also diamagnetic. So after all, it does make sense that the blood is repelled by a magnet. The conclusion is clear to me. The iron is not in a ferromagnetic state in the blood. Hope you learned something new in this video. I certainly did researching for it, and speaking of learning, I've got some good news for you. I found that the best way to learn more is to get my hands dirty and do some interesting experiments, some of which I have shared.
Here, we are going to discuss how the magnetic effect on blood. Firstly, I'm going to give a statistical data due to cardiovascular diseases. So that means due to cardiovascular diseases, according to WHO, so the year 2016, death in millions worldwide 17.9, and 2030 it's projected 23.6 million. So what are the cardiovascular diseases? Cardiovascular diseases are a group of disorder of the heart and a blood vessel, and they include coronary heart diseases, peripheral arterial diseases, rheumatic heart diseases, congenital heart diseases. So that means treatment of cardiovascular disease, surgery, medication, cardiac. So that means this is the treatment of the cardiovascular diseases. Side effect of heart disease medication. So swelling tongue, diarrhea, high blood potassium level, low blood pressure, intestine bleeding, kidney diseases, vomiting blood, trouble breathing, gangrene, and depression. So that these are the side effects. So that means for this side effect, So that means we are trying to form we are trying to form a mathematical model. So with the help of mathematical model, so we try to diagnosis. So that means firstly I'm going to give you introduction. What is the introduction? What we have done. It is well known that stenosis is responsible for many cardiovascular diseases. The injury in artery known as arteriolysis, which is the uneven flow of the blood. This problem can be reduced by applying magnetic field in stipulated way to reduce the shear parameter of the artery and change the speed of the blood. In our study, we have considered Bingham plastic fluid model condition as a reference in order to study non-Newton character of blood in presence of applying magnetic field. First thing, what do you mean by the stenosis? What is the, that means here, stenosis is the main responsible for cardiovascular diseases. So that means, first I'm going to give a definition of blood. So what do you mean by the blood? Blood is a fluid that carry oxygen and nutrition to the cell and carry out carbon dioxide. It is also called in tissue. Why it is called in tissue? Because a specialized cell that serves a particular function. So that means stenosis. I'm going to give you the definition of stenosis. So what do you mean by the stenosis? The abnormal narrowing passes of a body, that is called a stenosis. So that means if it stenosis happen in any artery, the blood will not flow. So due to that, some problem will take place. That is heart attack, congenital heart attack, coronary heart disease. These things will happen. So that means my aim is to what I have to develop one mathematical model. So with the help of that mathematical model, I try to diagnose that one. Try to diagnose that one. So that means with the help of simple differential equation, I'm trying to form a mathematical model. This is the simple partial differential equation minus del n del eta del z u mu by r del by del r del mu z del r. This is a simple partial differential equation. This is a simple partial differentiation. With the help of this differential equation, I'm applying only one part here. That part is what? Sigma d square u. So that means this portion I'm applying here. So this is the nothing but an equation of continuity. So sigma be the what? Permeability constant, b with the magnetic field, u with the axial velocity, r with the radial coordinate. So that means this is the formation. This is the governing equation I have taken. So with the help of this governing equation, I try to form a mathematical model. So with the help of that, I try my best to control the blood flow. So if I try my best to control the blood flow, so that means I have tried my best to remove the stenosis position. So firstly, I'm going to give you the definition. What do you mean the arteries? Arteries are the blood vessels that deliver oxygen-rich blood from heart to the tissue of the body. There are different types of arteries. Number one artery is carotid, aorta, coronary, femoral, arterial. These are the different types of arteries. So that means in the arteries, the stenosis will take place. Just see. So that means how much intensity, magnetic intensity can a human body can take. So according to the Alexander Legros, a medical biophysicist at the Lawson Health Research Institute and Western University in London, Ontario, and UTIC scientists, the smallest magnetic field that has a reliable have been shown to trigger a response in a human is around 10,000 to 20,000 micro Tesla. So that means here I'm applying the magnetic field. So here I'm applying the magnetic field. The intensity is 246 Tesla. So this is the geometry. This is the geometry of the arterial segment. So suppose this is an artery. So that means this is the artery through where the blood is free flowing through it. So this is the stenosis position. That means the constriction takes place, then blockage takes place. So the height of the stenosis is what? Delta. So the height of the stenosis I'm taking here what? Delta. So that means my aim is to what? I have to minimize this portion. So if I minimize this portion, the blood will flow. And if blood will flow, then my work is over. So for that one, I have taken that the governing equation, and I have taken the what? Bingham plastic fluid model also. The formulation. So that means the governing equation I have taken that can be converted into non-dimensional parameter because there is different parameter, x parameter is there. So we are going to remove that parameter. That's why we are making this in non-dimensional form. So with the help of equation 1, so this is a what? Equation 1, and this is equation 2. So with the help of equation and equation 2, we are formulating a new equation. That equation will be this one. So that means firstly I'm getting is a partial differential equation. I'm getting an ordinary differential equation. So I'm transforming that equation with the help of what? Some transformation, for example, Laplace transformation we are applying here. So with the help of that one, I'm getting a new equation. That new equation will be this one. So minus d eta by dz 1 by lr r d by dr r tau z plus a square lr. So first, what is lr? What is h? H be the Hartmann number. What is h? H be the Hartmann number. And what is l? L be the Reynolds number. So what is Hartmann number? I'm going to give you the definition. Hartmann number is the ratio of the electromagnetic force to the viscous force. What do you mean by the Reynolds number? Reynolds number help provide flow pattern in different fluid flow situation. So that means here we are taking the blood. So we are considering blood as a non-Newtonian fluid. So why we are considering non-Newtonian? Because it does not satisfy the Newton law of viscosity. I'm going to give you some example of non-Newtonian fluids. So non-Newtonian fluids are what? Ketchup, blood, these are the non-Newtonian, and some of the Newtonians of water, milk, these are the what? Newtonian. So that means I formulated this equation. So I'm now going to solve this equation. So that means, so now equation 3 is converted again non-dimensional parameters. So if I convert it into non-dimensional parameter using Hartmann numbers and Reynolds number, it gives you this equation. The equation is in this form: r square d square u by z by dr square plus du z by dr is equal to kr square. What is k? Is equal to this one. K is equal to this one. So this is a second order differential equation. So I'm going to solve the second order differential equation with the help of r is equal to e to the power z I'm considering. So after that I'm getting the equation will be, after that I'm solving the equation, I'm getting the axial velocity will be this one. So we know the shear parameter, shear pressure segment will be Tz will be given, always given by this formula. Always given by this formula. Tz is equal to mu du z by dr. So now I'm using the Bingham plastic fluid model. So with the help of Bingham plastic fluid model and governing equation, that is equation of continuity. So with the help of this one, I'm formulating the mathematical model. Yes. So firstly, again, I'm going to give you the definition. What do you mean by the Bingham plastic fluid model? Bingham plastic is a viscoplastic metal that behaves as a fluid body at a low stress, but flow as a viscous fluid at a higher stress. For example, mud, toothpaste, chocolate. These are all Bingham plastic fluid model. So that means here, this is the equation. So I'm putting the value here from this equation. From this equation, use it, I'm differentiating from here. So that means uz is given here. So that means I'm differentiating again, substituting. After simplification, I'm getting this one. So with the help of some boundary condition, uz, that means I'm taking the value in between r0 and r is equal to r0 to r0. So that means with the help of this one, I'm again finding the volumetric flow rate. So what is the volumetric flow rate? The volumetric flow rate is always given by this formula. Q is equal to r0 to r twice by r uz here. So what is uz? So here, from here we can get the value of uz. So this is the uz. So I'm putting here uz and I'm integrating with respect to what r. So that means if I integrate, I'm getting the value of q will be this one. So that means Q, what is the value of Q now? That means Q be the volumetric rate flow, and Q is always given by this equation. So that means these are the known parameters. C be the pressure gradient, and if I put the value, so you can get the value of Q. So that means if the value of Q, and I'm substituting that value graphically. So if I put the graphically, so I'm getting some different curve. So with the help of different curves, so I'm analyzing, so we can conclude from there whether it is in blood is free flowing or free flowing through it or not. So again, I'm finding out the apparent viscosity. So how does viscosity affect blood flow? So that means increased viscosity increase the resistance to blood flow and thereby increase the work of the heart. So what do you mean by the blood viscosity? Blood viscosity means what? We have to measure the thickness and stiffness of an individual blood. So that means this how viscosity works in a blood flow. So that means this is the mathematical expression mu is equal to this one. So that means I'm considering T beta will be this one. So that means again I'm simplifying. After that I'm getting the value is in the form of uz is equal to this one. So now I'm representing this one graphically. So that means what is the graphical representation? The graphical representation will be this in this form. So that means this is the graphical representation. So it shows in a parabolic. Say plus stenosis now. This shows a parabolic. If it is in parabolic, it means that blood is free flowing through it. Free flowing through it. So that means this is the another graph, flow resistance variation with stenosis height. So if I put the different values of n, if I put the value different values of u, and if I put the different values of del by r, I am getting the stenosis height in this way. So that means here I am seeing the planted position. So if it is in planted position, what do you mean by the statement? It means that the fluid which I have taken, it is in what? Non-linear. From here we can conclude that we are getting one conclusion that if the magnet is applied in a blood flow, it's work on it. So that means we can someday minimize the stenosis position. That means we are free from the medication. So the medication gives side effect. So if I apply this one, so it gives us no side effects. So that means it is easier for too long live. So this is my blood flow representation. So again I'm going to see one video. Just see this one, whether it is audible or not. Just tell me.
Hello everyone. Probably during your childhood you were told that you should eat apples because they have many vitamins and nutrients, including iron. But have you ever wondered what happens if we put a magnet close to this fruit? Well, we think that it's a very interesting question. Usually magnets attract metals, and the iron in apples should be no exception. In this video we'll see if there's a magnetic attraction between this fruit and a cube magnet. Well, what happens if we put a magnet close to an apple? Let's get it on. We must say that this experiment was first shown on television in a popular TV show, but we hadn't the time to repeat it and test it until now. We remembered this experiment not long ago, and we were curious to know if what we saw then is true or not. Surely you're already anxious to see it. Keep calm, we're about to show you. This experiment is quite simple. All you need is a neodymium magnet, 2 apples, a string and a stick to balance the fruits. To begin, you need to tie one side of the rope to something heavy to create some sort of counterweight. If you're going to repeat the experiment at home, do a strong knot, since the weight of the apples can break the string and you'd have to start from scratch, and no one wants that. On the other side of the rope, tie the stick, trying to keep the knot right in the middle. This is done to perfectly balance the construction in case someone has not understood. We're almost ready for the magic. Place the 2 apples on each side of the stick. Balance the construction and wait for it to calm down and stop moving. Everything ready? Well, it's time to start. Take the magnet and approach it to the apple without touching it. And magic. You see? Real magic. Watch closely. The magnet is not touching the apple, but still the fruit begins to move little by little. Wow. But did you realize that the apple is not attracted but repelled by the magnet? We thought it to be the other way round, since in the television program we talked about, the apple was attracted by the magnet. We wanted to repeat it, but it seems they cheated us. The truth is, we don't know why this happens. It may seem silly, but we have tried with other species of apple and spinning the magnet, but nothing works. But even so, the mere fact that the apples react to the force of a magnet is a great discovery and a great achievement for us. By the way, you can be even more clever and increase the power of the magnet by adding smaller magnets. Let's try it. It works! Look, the apple's repelled with greater force than before. All this can be explained with science, but it's still difficult to believe what we see. In any case, the bigger the magnet, the more interesting the effect. So, did it work for you? If you didn't succeed in your attempt, do not be discouraged. Try it with other apples or magnets. Change the length of the rope and be careful not to breathe too hard when trying. If you do not get it anyway, keep trying as many times as possible. The magnet will not lose its strength and the fruits will not rot. Hopefully it'll work for you too, and your apples will move under the influence of your magnet.
Sarfraz, can you stop your video sharing?
Hello?
Huh. Thank you, Mr. Sarfraz Ahmed, for this informative lecture. Actually, yes, I have a general question. One more question I have. Sir, I have a general question. Tell about the subject mathematical biology. Safas, are you getting my voice?
Hello? I'm not getting your voice.
Are you? Yes.
Hello?
So someone is asking a general question. Tell about the subject mathematical biology. He is actually asking about the subject mathematical biology.
What?
Mathematical biology.
Sir, I have a general question. Tell about mathematical biology. So that means you interrelated mathematics with the biology. So after that, what you can get, that is a mathematical biology. So here I'm using differential equation. That means partial differential equation. So with the help of partial differential equation, I am developing a mathematical model. So that means that mathematical model is nothing. It comes from the what? Biology, no. So that means blood flow is there, so biology will be there. So that means I'm interrelated match with the biology. So that's why you can get a mathematical biology.
Sir, the best book for differential equation, please.
Hello.
Can you also
Interrelated.
some books
Hello?
for differential equation? I think Dimpal's voice is not very clear. So there is a question. Suman Bhuya is asking, what are the best books for differential equations?
No, that means base books, we cannot say one base book. All are the base books. Somewhere something is good, somewhere something is best. So that means you just go through the every differential book. So the English set is best for you. So just see the books and choose it. So that means in some books, some topic is given very properly. In another book is given other topics properly. So you just go through it. So we cannot specify one name. That means differential which books is best. So that means I'm taking different books. So that means I cannot say that means this book is very good. Yes, you can. Hello, someone asking using differential you can also be used in physics, like to find the velocity sound waves in silly. Yes, it can be used. So that I'm not using this one, but it is possible. So here I'm taking one example now, Newton law of cooling. So that means there you can apply the differential equation. So you can find out, yeah, no problem. We can use that thing in the velocity to find the velocity sound wave in cylinder. Yes, it's may possible. Is yes, mathematical. So that means someone is asking that mathematical biology is a good topic to pursue research. Yes, it is very good nowadays. That means uh, it's that it is an era of biology. So that means human. That means everything is related with the human beings. No, COVID is there. So that means it's nothing but in biology. So that means you can pursue. So it is a very good. So that means now mathematical biology is very demandable nowadays. So that means you may go to pursue research on mathematical biology. So that means you just think of it. So that means lots of paper is there. So just go through it. So if you have any problem, you can contact me also. There's no problem at all. We are going to help you. Suresh Mandal. Oh yes, I'm going to share your PPT and you just give me your mail ID. So I'm going to send your PPT and video.
So Dimpal, if you'd like
Yes,
to.
I'm going to Dipanjal Ghosh. So that means I'm going to give you. So just send me the mail ID. I'm going to give you. No problem. Suresh Mandal, na? So I'm going to
Okay,
give you my
I will share the
PPT. No problem.
PPT in general. If Sarfraz sir provide me, I can share in general. Actually, I
Hello?
can provide in the WhatsApp group also. We have no that issue.
It is over to convener Dimpal Jyoti Mahanta sir. So you can proceed now. I'll give my PPT to convener, sir. So that means you will share in our WhatsApp group. Okay.
Manjil, am I audible?
So my email ID is given in the first slide. So if you want this, just write down my email ID and send to me any message. So I'll give you. Dimple, can I show my PPT?
Yes, sure.
So write down everyone. My email ID is Sarfraz, Sarfraz, SARFRAZ. Write down SARFRAZ. Sarfraz Ahmed, AHMED, Ahmed. Dot, put one dot. Then JRT, J for Jorhat, JRT, @gmail.com. @gmail.com. Sarfraz Ahmed .jrt @gmail.com. Sarfraz, SARFRAZ. 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 Another mail address is Sarfraz @Kaziranga University.in. @Kaziranga University.in. Kaziranga University.in.
One thing you can do, you can please share the PPT. You can please share the PPT with me. Today.
Okay.
Now, Manjil, can you hear me?
Yes.
Okay. Actually, I don't know what is happening with my audio. Actually, this is because of the COVID. Actually, we have to say. Okay. Now, thank you, Mr. Sarfraz, for your very informative lecture. Now, with this, we are about to end our 3 days international webinar on fundamental mathematics. But before concluding this session, I would like to request Dr. Manjil to say a few words.
So thank you so much, Dr. Mahanta. So it was a very nice session, and I would like to specially thank all the participants for sticking to the very end. So we had some problems in the beginning, in the first day, and we have managed to solve that issue now. So I thank the participants for their patience. And I would like to thank the speakers, Dr. Gautam Kolita, who gave the first lecture, and Mr. Sarfraz Ahmed for today's talk. And also thank the entire Kaziranga University family, especially the Vice Chancellor, Professor P.K. Misra, then the Dean of School of Basic Sciences, who was with us in the first lecture, and Dr. Dimpal Jyoti Mahanta and Dr. Jayanto Bhattacharjee, who has been working behind the scenes to make this successful event. So thank you, everyone. So
okay, thank you, Manjil. So again, before concluding this event, on behalf of the entire organizing team, I feel very privileged to give a vote of thanks on this occasion. First of all, I would like to thank all the participants for your kind cooperation and help to make this event a grand successful one. I would like to thank Ganit Sora and Assam Kaziranga University to give us this opportunity to host this international event. A special thanks to Dr. Manjil Saikia for your continuous effort and dedication to make this event a great successful one. Thank you so much, Dr. Manjil. I also like to thank Dr. Gautam Kolita, Mr. Sarfraz Ahmed, and Dr. Manjil Saikia for your energetic and very informative and extremely valuable sessions. I would like to thank Professor Bhabakumar Sharma sir from IIT Guwahati, Professor P.K. Mishra sir, Vice Chancellor Assam Kaziranga University, for your prestigious times and beautiful words during the inaugural session. I would also like to thank Professor Jayanta Kumar Sharma sir, Dean School of Basic Sciences, School of the Assam Kaziranga University, for your constant guidance. Thank you so much, sir. I would also like to give a special thanks to the members of Department of Mathematics, Kaziranga University, who are actually behind the scene, Dr. Biju Kumar Datta, Dr. Jayanta Bhattacharya, Dr. Pallavi Saikia, Mr. Sarfraz Ahmed, and the students of Department of Mathematics, and also I'm very thankful to the alumni of our department. Without your constant support and guidance, it's not possible for us to organize such a successful event like this. I would also like to thank all the members of School of Basic Sciences, Assam Kaziranga University, for your advices and suggestions from all the directions. I also like to thank the Deborah Dayan team, Paras Dayan team, Manas Monalisa Rasnibar, and all the people associated with the event for your supports during this international webinar. Thank you so much to all of you. With this, I conclude the vote of thanks, and over to you, Dr. Monty.
So I think there is nothing more to add, and we can now stop the stream.
Okay.